Today we're going to look at Taylor series, and we start out a Taylor series exactly the same way that we would start out a Taylor polynomial. As a matter of fact, we're going to look at the terms of a Taylor polynomial and then eventually write the nth term and then write that as an infinite series. If c equals 0, the series is called a Maclaurin series. Find a Taylor series for f of x equals e to the 5x centered at c equals 2. Give the first four non-zero terms and the general term. We have f of 0. That's equal to e to the 5x. And then when we evaluate this at 0, we'll have e to the 0, which is 1. Then the first derivative is e to the 5x times 5. E to the 0 is 1, so then we have 5. The second derivative at 0 is 25e to the 5x. E to the 0 is 1, and then 25 times 1 is 25. To get four non-zero terms, we have to take one more derivative. That's going to be 125e to the 5x. When we plug 0 in, we get 1 times 125, which is 125. Now, in this case, the third degree polynomial of not 0 now, because we're writing the polynomial, we have the third degree polynomial of x is equal to, and we want the first four non-zero terms, and the third degree will give us 1, 2, 3, 4 non-zero terms. We have 1 plus 5x plus 25x squared over 2 factorial plus 125x to the third over 3 factorial. Now we can write dot, 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 and the general term is, let's see, it's going powers of 5. That'd be 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, and so on. We have 5 to the n. We also have x to the n. And that is divided by 0, 1, 2, 3 factorial. That is n factorial. And we don't usually write the 0 and the 1 factorial. We can write that as an infinite series by using summation notation. We have n equals 0 to infinity of 5 to the n, x to the n over n factorial. Let's look at the power series. The power series comes from the function 1 over 1 minus x. Now that is equal to 1 minus x to the negative 1. And you get the power series from the Maclaurin series. So we're going to center this at 0. If I plug 0 into this one, I get 1 minus 0 to the negative 1. That's 1 to the negative 1, and 1 to any power is 1. The first derivative is negative 1 times 1 minus x to the negative 2, but then we multiply, remember the chain rule, times negative 1. That'll make that positive. And then we're centering this around 0. That means we have 1 times 1 minus 0 to the negative 2, and all of these parentheses end up being 1. So this one is also 1. The second derivative is negative 2 times 1 minus x to the negative 3, but times negative 1 makes that positive. And then the parentheses will be 1, 1 to the negative 3 is 1. Next coefficient is 2. The third derivative is negative 6 times 1 minus x to the negative 4 times negative 1, which makes that positive 6. Then when we plug 0 in, we get positive 6. And then let's do one more. The fourth derivative is negative 24 times 1 minus x to the negative 5, but then times negative 1, making that positive 24. So we have 24. The power series, the polynomial for the power series is p sub, in this case we did 4 derivatives, of x is equal to 1 plus x, because the first coefficient is 1, second coefficient is 1, third coefficient is 2. We have plus 2x squared over 2 factorial, plus the next coefficient is 6, x to the third over 3 factorial, and then plus we have 24, x to the fourth over 4 factorial. Let's simplify that. And what we get is 1 plus x plus 2 divided by 2 is 1, so we have x squared. 3 factorial is 6, so now we have 6 divided by 6, that's 1. and that's x to the third. 4 factorial is 24. 24 divided by 24 is 1, and that'll happen infinitely. The coefficients will match up with the factorials, and all of the coefficients end up being 1. Well, the nth term is just x to the nth. If we write that as an infinite series, we have n equals 0 to infinity of x to the nth. And that's why it's called a power series, because it's just the number to a power. Now, the amazing thing about this is that it conforms really super close between -1 and 1. Here I've plotted the actual function right here. And that is actually the thin line. And the thin line has an asymptote at 1, a vertical asymptote, because 1 makes the denominator 0. And there's a little piece of it over here too. Now I plotted 1, 2, 3 terms of our Taylor polynomial here. Actually, it's a Maclaurin polynomial, and that's the thick curve. And now here's an x squared, so you expect that parabola. And it mimics the power function, 1 over 1 minus x, very closely between -1 and 1. But once it gets less than -1 and greater than -1, it really starts to curve away and it starts to fail. Here I've plotted all the way up to x to the 5th, and it's really fitting it very well in between -1 and 1, but you see it still fails after -1 and 1. And no matter how many we plug in, I go all the way up to x to the 7th, it's still starting to fail at -1 and 1. Well, think about your geometric series, the test that we have for it. This is a geometric series where a sub 1 is equal to 1 and r is equal to x. And we say, well, the absolute value of x has to be less than 1 in order for this to converge. So x has to be between -1 and 1 for us to get good approximations. If we go outside of that, this function starts to fail. And we even see that when we start graphing these. There are 3 special Maclaurin series you must know. These are the series for e to the x, sine of x, and cosine of x. To derive a series for e to the x, we do f of x is equal to e to the x, and we're doing Maclaurin series for these. That's what you have to memorize. E to the 0 is 1, and then f prime of x is equal to e to the x. That's e to the 0. That's 1. The second derivative, actually we're doing this at 0, is e to the 0. That's e. That was e to the x. E to the 0 equals 1. They're all 1s. So the polynomial of nth degree, this is a Maclaurin polynomial, is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus, keep on doing that forever, and you know all the coefficients are going to be 1. So the nth term is x to the n over n factorial, and then the series is n equals 0 to infinity of x to the n over n factorial. That's the Maclaurin series for e to the x. If we start plotting the terms of the polynomial, we can see where the solid line or the thick line is fitting the skinnier line, the thinner line. And the more terms that we add, the farther it is fitting to the curve. So this one is, it converges everywhere. Converges for all values. Not just from -1 to 1, but for all values. Let's derive the series for sine of x. We have f of x is equal to sine of x. Let's plug 0 in. Sine of 0 is equal to 0. F prime of x is cosine of x. That's cosine of 0, and that's 1. The second derivative is negative sine of x, and that is negative sine of 0, which is 0. The third derivative is going to be negative cosine of x, and negative cosine of 0. Cosine of 0 is 1, so we have negative 1. Fourth derivative is going to be sine of x, and sine of 0 is 0. Now we're back to where we started. So then it's going to go 1, 0, negative 1, 0, and we'll keep going in that pattern. The polynomial, not fourth, but we want nth here, of x equals. We start with 0 and then 1x. And then we have, this is a power of 0, this is the power of 1, this is the power of 2, 3, 4, 5, 6, 7, 8. Keep going on in that pattern. You can notice that all of the even powers are going to be 0. We're just left with the odd powers, and then those will alternate signs. So we have minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, minus x to the 7th over 7 factorial, and so on. Now let's write the nth term. Well, these are odd powers, 1, 3, 5, 7. I can write that as x to the 2n minus 1 over 2n minus 1 factorial, because the denominators, they're also odd values, but they're the odd factorials. Keep on going with that. Then the series is n equals 1 to infinity. If I write 2n minus 1, I need the first power to be 1. So then we have 2 minus 1, that power is 1. I'll need to use 1 to start this one. And this is x to the 2n minus 1 over 2n minus 1 factorial. A great way to remember this, that you use the odd powers, is sine is odd. Here is the graph of sine, very roughly. Sine is an odd function because it is symmetric about the origin. If you pick a point on the left side of the origin, go through the origin, you're going to find its corresponding value. Sine is an odd function, so in the series, you only have the odd powers. Let's look at starting to graph more and more terms of sine, and you can see that it fits in between the top and the bottom right here. And then as you add more terms, it's fitting more and more of the graph. And when you go to the 11th, look how much it fits. And sine converges for all values, or we say it converges for all reals. Not just negative 1 to 1 like we have with the power series, but if you add enough terms, you will fit most of the graph. You can't fit the entire graph. We can't actually go to infinity, but in theory, if we could fit the entire graph, all reals. Let's derive the series for cosine. We have f of 0. We're doing this at 0. F of 0 of cosine of x is cosine of 0. That's 1. F prime of 0 is negative sine of x. That's negative sine of 0, and that is 0. Second derivative of 0 is negative cosine of x, and that's negative cosine of 0. That is going to be negative 1. The third derivative is going to be sine of x, which is, we're evaluating that at 0. That's 0. The fourth derivative is cosine of x, and we have cosine of 0, that is 1, and we're back to where we started. So that goes 0, negative 1, 0, 1, 0, negative 1. You'll keep doing that forever. So let's look at the Taylor Polynomial. We have 1, and then minus x squared over 2 factorial. Then we have a 0. Then we have plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and then that process will repeat. Well, those are the even powers, and we have x to the 0 right here. That's even also. So we have x to the 2n over 2n factorial. We can write that as an infinite series. We can go n equals 0 to infinity of x to the 2n over 2n factorial. Cosine converges on all reals as well. A great way to remember this is that cosine is an even function. If we graph cosine, there it is very roughly. If you pick one point on the left side of the y-axis and you reflect it over the y-axis, you have the corresponding value. Cosine is an even function, and we have the even powers in the series. We can manipulate these three special series, or any series we are given, to find other series by using the following techniques. We can substitute into the series, multiply or divide the series by a constant and or a variable, add or subtract two series, and we can even differentiate or integrate a series. Find a Maclaurin series for f of x equals sine x squared. Well, sine of x is equal to, I need the odd powers, so x to the first minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus, keep on going in that matter. And there's sine of x, but we've plugged x squared in for x. Now I have to plug x squared in for all of these. Sine of x squared is equal to x squared minus x squared to the third. X squared raised to the third power is x to the sixth. So we have x to the sixth over 3 factorial plus x to now to the 10th over 3 factorial and minus x to the 14th over 7 factorial plus, keep on going. Now we want to write the nth term. And I notice that the powers of x start with 2 and they keep increasing by 4. That means we have x to the 4n. But if I plug 1 in here, I get 4. So what if I plug 0 in here? I could plug 0 and then I would have to add 2. And that's over. We have 3 factorial. Oh, this should be 5 factorial. And I notice that the denominators are still odd. That hasn't changed. That's 5 factorial. And if I start this at 0, then I have to start the denominator, or n at 0 for everything. Now those are odd, so I'll have 2n plus 1 factorial if I'm going to start this at 0. Now the Maclaurin series is n equals 0 to infinity of x to the 4n plus 2 over 2n plus 1 factorial. Find a Maclaurin series for f of x equals x times cosine of x. Cosine of x is equal to, I need the odd powers now, we have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and keep on going. Well, to get x times cosine of x, I just multiply everybody by x. That'll be x minus x to the third plus x to the fifth minus x to the seventh, and then we have over 2 factorial over 4 factorial and over 6 factorial plus, keep on going. Well, let's find the nth term. I see that I have 1, 3, 5, 7. Those are odd powers. X to the 2n plus 1. If I do 2n plus 1, that means I'm starting n at 0. And that's over, I have 0 factorial, 2 factorial, 4 factorial. Those are even. So we have 2n factorial. Then the series is n equals 0 to infinity of x to the 2n plus 1 over 2n factorial. Let's start out with e to the x. E to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. And we can keep on going in that matter. Now, we've replaced x with 2x. We have e to the 2x is equal to 1 plus 2x plus, now remember, if I plug 2x in for x and it's squared, like right here, that's going to be 4x squared. That's over 2 factorial, and then plus 8x to the third over 3 factorial. Remember, we took 2 to the third, that's 8, and then 2 to the fourth is 16, x to the fourth over 4 factorial, plus, keep on going. The nth term is 2 to the n if I start at 0, because that's 2 to the 0, 2 to the first, 2 squared, 2 to the third, and so on. And then we have x to the n, x to the 0, x to the 1, x to the 2, and then that's all over. We have 0 factorial, 1 factorial, 2 factorial, so that's n factorial. The series is n equals 0 to infinity of 2 to the n, x to the n over n factorial, and we could probably write that as 2x to the n. In letter B, use your answer to A to find a Maclaurin series for the function h. Given that h prime of x equals e to the 2x, so e to the 2x is h prime of x. These terms right here are going to represent h prime of x. We want to know what h of x is. H of x equals, now if that's the derivative, we want to back up to the function. We're going to integrate all of this. When you integrate, you'll end up with plus c, and we like to put c at the very beginning of series instead of at the end like we do with normal functions. We have c plus. The integral of 1 is x. The integral of 2x is x squared. The integral of x squared is 1/3 x to the third. And constants, the 4 over 2 factorial, they just follow along. When we integrate, constants always just follow along. Then we have plus x to the fourth times 1/4. That's the integral of x to the third. And then the 8 over 3 factorial tags along. Then we have x to the fifth times 1/5. That's the integral of x to the fourth. And 16 over 4 factorial. It tags along as well. Let's see if we can find a pattern going on here. We have h of x is equal to c plus x squared plus 4x to the third over, 1 times 2 is 2 factorial, and then times 3, we could write that as 3 factorial. And then we have 8x to the fourth over, that can be combined to be 4 factorial. And then we have 16x to the fifth over 5 factorial. And we can keep going in that manner. And then, we need to find out what c is. We know that h of 0 equals 3, and if we plug 0 into all of these, they will all be 0. H of 0 is equal to 3. The constant is 3. H of x is equal to 3 plus x squared plus 4x to the third over 3 factorial plus 8x to the fourth over 4 factorial plus, keep on going in that manner, plus keep on going forever. Now let's see if we can write the nth term for this. In order to really get the pattern on this one, we're going to have to manipulate this one because I have nothing in the denominator here, and it'd be really nice if I could have 2 over 2 factorial, which is 2 over 2, which is like multiplying x squared times 1, which is perfectly legal. Let's write the series, and the series is really nice for this much right there. And the 3 really doesn't fit in the pattern very well, but that's all right. We can actually cheat a little bit and write 3 plus. And then we have x to the n, and out front we have 2 to the n. We have 2 to the 0, 2 to the first, 2 squared. So we have n equals 0 to infinity. Now if we're going to start this at 0, we want the first one to be 1. That's going to have to be n plus 1. And then it's all over n plus 1 factorial. And there we have it.